Okay, good morning and welcome to the five videos total, walking you through the notes. Again, you can look at Bozeman physics if you want a similar sort of note. So optics are going to look at how the behavior of light when it interacts with matter. And our most common forms of optics that we'll take a look at in here is reflection and refraction. Just a quick refresher about light in general. Remember, light is an electromagnetic wave. You studied this last year, Mr. Horgan, in the waves unit. Remember, we classify electromagnetic waves as such because they do not require a medium to move. It's really oscillating electric fields and magnetic fields. And again, we'll study that in more detail when we get to magnetism. But remember, we have a wide variety of electromagnetic waves: radio waves, microwaves, infrared, visible light, ultraviolet, X-ray, and gamma. These are classified by wavelength, and that's how we talked about last year. Technically, it's actually classified by frequency, and we'll make that distinction in just a little bit. A couple things about these waves. First of all, obviously, they do not require a medium to travel. They can travel through a medium, but they don't need one. The other thing to remember is that the speed of light is a fixed value in vacuum. So in empty space, it travels 3 times 10 to the 8 meters per second, or an incredible 186,000 miles per second. And again, we'll talk about that a little bit later as well. All of this is considered to be light in physics. We talk about visible light and all these other types of forms of radiation we also describe as light. Now, these are Maxwell's equations. You do not need to know these. These are the calculus derivations, and we may talk about them briefly, but it's not something you need to know. They're related to electric fields and magnetic fields. Again, these are the calculus derivations. We also talked about you have an oscillating electric field, and at the same time you have an oscillating magnetic field perpendicular to each other. That's what makes up an electromagnetic wave, and the wave propagates in this direction at the speed of light through vacuum. A couple of quick things that are very important in our study of optics is, remember, your eyes collect light. Your eyes do not send out light. So when you're doing ray diagrams, and I know you know this, but make sure that the arrows are always pointing towards the eyes, not away. So cats don't send out light, and baby eyes don't do the same. Now, a couple things. When you look at something, why do we see something? So here's a 3-person horse. I think that's Photoshop, but anyway. Why do you see that? Well, here in physics is the international symbol for the eyeball. Here's a light source. And remember what's actually happening is light is leaving the object, it's striking the horse, bounces off and comes to your eye, or pretty close to your eye. Again, we put an arrow on that. That means the light leaves the source, hits the object, bounces to your eye, your brain sees that light arrive, and it detects the object and says, oh, horse. If you don't have the light source, or if the light doesn't bounce to your eye, you don't see it. And again, that sounds obvious, but that's kind of important for something we'll talk about later. As I just mentioned, sometimes we say that we classify light by wavelength, and when we talk about color, typically they say red has a long wavelength, and violet has a short wavelength, and green has a medium wavelength. That's fine. You can talk about it that way, but I really want you to think about frequency. So red has a very low frequency, green has a medium frequency, and blue or violet has a very high frequency. The equation for the speed of light and the other variables we talked about, and again, we did this last year in the Ripple Tank lab. We say velocity is distance over time. Well, with waves, distance is wavelength, and time is the period of oscillation, like the pendulum. And we can say the period of oscillation and frequency are inverses. So this is the equation I'd like you to know. That for light, the V is really C. It's that constant. The wavelength times the frequency is the speed of light. And again, we'll come back to this a little bit later. So, for example, Pink Floyd's famous album cover, Dark Side of the Moon, white light goes into a prism. It actually does a process known as dispersion, also refraction, and it splits the light into component colors. So white light is really all of the Roy G. Biv colors mixed together. So when you see this lovely duct tape blue dress, it's blue because white light strikes it. All the other colors are absorbed except for blue. Blue reflects to your eye. You see blue. This dress reflects red light. This dress, although a little disturbing, reflects all colors of light. So white light hits, all the white light is reflected, you see white. This garbage bag black dress reflects none of the light. So black really isn't a color, it's the absence of color. White is all the colors mixed together. So again, we're going to take a look at reflection and refraction. So today we'll concentrate on reflection. Now reflection simply means that when a wave or light bounces off a boundary or surface. So it hits the boundary, does not pass through, and it comes back out. You've seen this before. Every morning you stand in front of a mirror, you look in the mirror. You don't see yourself, you actually see your image. It's an optical representation of you. It looks like you're standing behind the mirror. You're not, obviously. So we say we see the image of the person with a flat mirror. There's an activity you may have done before. It's something I do in lab. You write your name on a piece of paper, you hold the mirror up, and you try to recreate the tracing. And we may do that in class, so if it's a little confusing, it's the old writing in a mirror trick. What I really want to talk about is the types of images. And this gets a little confusing. You're really not going to know what this means until we get in the lab. But when you look at an image, there's two types of images. There's virtual images, and there are real images. Virtual images are what you see in a flat mirror. So an object stands in front of the mirror, the light hits the mirror, bounces off, comes to your eye, and your brain looks at this and goes, oh, this light came from behind the mirror. It looks like it was behind the mirror. So when you stand in front of a flat mirror and look at an object in a mirror, it looks like the light is coming from behind, but it's really bouncing off the mirror and coming to you. The light rays appear to be diverging. They're moving away from each other. So we say that the image is formed by diverging light rays, and it cannot be projected onto a screen. This will make sense when we get in the lab. So here's an object standing from a curved mirror, in this case a concave mirror. Light hits the mirror, bounces off, comes straight to your eye, and you can actually project this onto a screen. So instead of going into your eye like it was over here, it's going onto a screen. You can actually look at the screen and see it. Also notice that the light rays appear to be converging. They're coming towards each other. So we say the real images formed images by light rays converging together, and they can be projected onto a screen. And again, this will make much more sense after we do the lab. The other thing we have to pay attention to is the way we describe images. So we can say images are inverted or flipped upside down. You may have seen this before when you look in a spoon, for example. You may see your face is upside down. So if it's flipped over, we say it's inverted. If it's upright or erect, I prefer to use the term upright. It means the orientation of the object is the same as the orientation of the image. So that's one thing we talk about. The other thing is the size. When you stand in front of the mirror in the morning, you're the same size as the image. Sometimes mirrors can make things look smaller, and sometimes mirrors can make things look larger. So we take a look at the size. Now, a really important concept with mirrors. Here's a mirror down here. We're going to shine light on the mirror. The light is going to hit the mirror and bounce off. And as you probably suspect, the angle at which the light ray comes off is the same as the angle it went in. In optics, it's important to remember that angles are always measured relative to a normal line. So again, if this is the boundary, if this is, for example, a lake surface, we actually take a normal line, which a normal, of course, just means perpendicular. So we have a perpendicular line hitting this boundary. The light ray comes in an angle which we call the angle of incidence. It's some number. Here it looks like it's about 60 degrees. And the light will reflect off at the exact same angle, the angle of reflection. It's very tempting to take the angle that it's coming in relative to the mirror. You can't do that. And you'll see why. It's tied to a mathematical function when we do the equation. So the angle of incidence is between the incoming light ray and the normal line. The angle of reflection is between the normal line and the reflected ray. And again, it's always measured relative to normal. If you see this, if you play any sports, you know this. By the way, this is called the law of reflection. Angle of incidence equals the angle of reflection. If you play tennis, you manipulate your racket to reflect the ball at a certain angle. When you shoot a basket, you bounce off the backboard. You kind of intuitively get that. Here in hockey, they're showing a guy passing a puck off the boards to a teammate or down the ice. They've labeled this incorrectly, not physics way. They've used the angle between the reflecting surface. It really should have a normal line coming out here. We'd have the angle of incidence and the angle of reflection. So again, just be aware of that. There's a really nice animation online, and again, we'll do some of this stuff in lab, but there's a nice animation showing you this. Last year in the Ripple tank, you had light waves or wave fronts coming in, hitting a boundary and bouncing off. So you had water waves hitting the side of the tank and they were bounced off. It's a lot more convenient in optics to replace these parallel wave fronts. This might represent, for example, these blue lines might represent the crest. In between would be the trough, crest, trough, crest, trough. It's a real hassle to draw this. So we find it's easier to actually just draw the rays. So this light ray is an incoming light ray, instant light ray, hits the boundary, comes off. I can put it in the normal line and I can put in the angles. And then you can manipulate the angle. So again, it comes in at 45, leaves at 45 relative to the normal line. We can change that to a very small angle. It's coming in almost vertically. If I take and bounce a basketball off the floor, bounces straight in, the angle is 0. Comes in along normal line, comes out at the normal line. This would be like skipping a rock off a pond. Very, very high angle, skips, goes off. So again, nice way of thinking about the picture. There's a flat mirror lab we sometimes do in class. We don't really need to. It's not something that the AP asks. But the key thing about flat mirrors and you'll see this is different for curved mirrors. Flat mirrors, the images are always virtual. They look like they came from behind the mirror. They're always upright and they're always the same size. And again, you always look in a flat mirror every morning when you get dressed or you're doing your makeup or checking your hair or whatever you do. You're not really behind the mirror. You look upright and you look the same size. Okay, we'll talk about curved mirrors a little bit later. So that concludes our first video.